Hello everyone, this is Babitha, working as Assistant Professor in the Department of EC in Institute of Aeronautical Engineering. In this session, I am going to discuss about problems related to the operational amplifier differentiator. So before going to the problem, just I'll revise the operational amplifier differentiator. What is the basic function of operational amplifier differentiator circuit? So generally, if we take the normal differentiator circuit, we can design by using the capacitor as well as the resistance circuit. So for this, we can provide the input signal and we will get the corresponding output signal. So here the input signal, maybe we can take it as the sinusoidal signal or square wave signal or triangular wave signal or else step signal also. We can apply any kind of sinusoidal as well as non-sinusoidal signals we can apply to the differentiator circuit. So across the output of this one, we will get it as differentiation of applied input signal. Okay. So by using only passive elements, that is resistor as well as capacitor, we can able to design the differentiator. So it can able to perform the differentiation operation with the time constant RC here. Okay, so the time constant of this particular circuit is depending upon how much amount of capacitance we are choosing here and how much amount of resistance we are choosing in order to design this particular circuit. And depends upon that RC values only, the time constant of the circuit will be changed. Okay, so if these values are high, means it will take very high time period to differentiate the applied input signal. If these values are less, means it will take less time to differentiate the given signal. So this same differentiator circuit we can also design by using the operational amplifier as the active device. So I am taking first operational amplifier with the inverting as well as non-inverting terminal as the two inputs, and for the positive input I am grounding here, and for the negative input or inverting terminal I am connecting one capacitor, and the feedback I am giving through the resistance RF. This is C1, this is RF, and here I am applying my input signal, and here I can measure my output signal. So in order to run this particular 741 operational amplifier, I need to apply the plus VCC as well as minus VEE supply voltages here. Okay, and in this case also we will get the output as minus RF C1 differential of VI signal. So here again RF C1 indicates the time constant of the circuit. Okay. So in this way we can design, or else in this way we can design. If we design with the resistor and capacitor circuit, we can call it as a passive differentiator circuit. And if we design with the operational amplifier along with the passive elements, means it is the active differentiator circuit, and it is providing the differentiation of the applied input signal. And in this case also we can take different types of inputs, either sinusoidal or non-sinusoidal type of inputs we can apply for this circuit also. But it is providing the differentiation of the applied input signal, that is well and good, but it is facing some problem at high frequency range of signals. So at high frequencies, it is going into the oscillations, it is breaking into oscillation and entered into the saturation region. So we cannot take out from that saturation region in the case of this particular ideal differentiator circuit. So in order to overcome that, we are moving for the practical differentiator circuit, and along with that the bandwidth provided by this ideal differentiator is also less. So in order to improve the bandwidth and to come out of that saturation level, we are moving for the practical differentiator. So how we can design this practical differentiator here means, for the ideal differentiator, the same ideal differentiator I am taking here, minus plus. For the inverting terminal, already we are having the capacitor, and RF and RF resistance. So this is the normal ideal integrator. So for this, to make it as the practical one, I am adding one extra resistance across the capacitor, that is R1, this is C1, and one more capacitor in the feedback, that is CF. And here we are going to apply our input signal, and across the non-inverting terminal we are providing the R compensation resistor. So this R compensation resistor is used to nullify the any biasing effects in the operational amplifier. Because of that reason, we are adding the R compensation. And the adding of this resistor R1 and capacitor CF will reduce the problem of frequency of oscillations in the output of the differentiator, and also improve the bandwidth of the differentiator. And for this circuit also, we need to provide the positive and negative supply voltages. So in the case of problems, most of the cases we will use this practical differentiator only, not the ideal. So this is about practical differentiator circuit. Now we'll move with the problems related to the practical differentiator circuit. So first problem is design a differentiator to differentiate an input signal that varies in frequency from 10 Hz to 1 kHz. If a sine wave of 1 volt peak at 1000 Hz is applied to this differentiator, draw the output waveform. So here in the problem, the given values are the input signal. Okay, input signal is varying from 10 Hz to 1 kHz. Okay, input signal is varying from 10 Hz to 1 kHz, and input signal we are taking here it as sine wave. So the range of the signal is 10 to 1 kHz. So within this particular range, we can choose any one frequency. So in the problem, they given the sine wave frequency as 1000 Hz, and 1 volt peak is nothing but peak voltage of the sine wave is 1 volt here. Okay, so this is the signal is given here. In order to differentiate this particular signal, we have to design the practical differentiator circuit. So for that purpose, we have to go with the practical differentiator circuit. So in that case, first step I am taking here it as the cutoff frequency of the practical differentiator circuit, that is FA. So that FA value is equal to the F maximum here. So F maximum is given in the problem, that is 1000 Hz. Okay, maximum value is given in the problem, that is 1000 Hz here. And the formula for this FA is 1 by 2 pi RF C1. Okay, this is the formula to calculate the cutoff frequency of the practical differentiator circuit. Okay, next I am considering my capacitor C1 value as 0.1 microfarads. So here we know the value of FA as well as C1, so that we can able to calculate the value of RF here. So from this I can calculate RF as FA equal to, the FA value is given as 1000 Hz. So 1000 is equal to 1 by 2 pi into RF value we don't know, into C1 is 0.1 into 10 power minus 6 farads. So from this we want to calculate the value of RF, that is equal to 1 by 2 pi into 1000 into 0.1 into 10 power minus 6. So if we solve this value, we will get it as 1.59 kilo ohms. So here we know the value of FA, C1 as well as RF here. So next I am letting the value of feedback resistance RF. So the feedback resistance RF I am taking here it as 1.5 kilo ohms. I am assuming this value to design the practical differentiator circuit. So here FB, the second cutoff frequency of the practical differentiator, it must be 20 times the first cutoff frequency FA. So FB equal to 20 FA. So that is nothing but FB equal to 20 into already FA value is 1 kilohertz. So that is nothing but 20 kilohertz. The value of FB is 20 kilohertz. And but what is the formula for this second cutoff frequency FB? FB equal to 1 by 2 pi R1C. So here we know the value of this R1 here. We have to calculate the value of C1 here. So for that I am taking here FB value is 20 kilohertz, that is 20 into 10 power 3 is equal to 1 by 2 pi into R1 is R1 value we don't know here, we have to calculate, and C1 value we have already assumed, that is 0.1 microfarads. So from this I can write R1 equal to 1 by 2 pi into 20 into 10 power 3 into 0.1 into 10 power minus 6. So if we simplify this, we will get it as 79.5 ohms. So I can approximate this particular value as 82 ohms. Okay. So we have calculated the R1 value also. Now we know the values of FA, FB, C1, RF and R1 values. So next we need to calculate the value of CF to design the differentiator. So how we can get that particular CF value? From the relation R1 C1 equal to RF CF relation, we can calculate this CF value here. So from this I can write CF is equal to R1 C1 by RF. So the value of R1 here it is 82 and C1 is 0.1 microfarads, that is 0.1 into 10 power minus 6, and RF value we have chosen here it as 1.5 kilo ohms. So CF. So after simplification, CF value we will get here it as 0.0055 microfarads. And next we need to calculate the value of R compensation also here. So generally R compensation value is the parallel combination of R1 as well as RF feedback resistance. So we can write it as R1 into RF by R1 plus RF. So R1 value we got here it as 82 ohms into RF value is 1.5 into 10 power 3 divided by 82 plus 1.5 into 10 power 3. So this value approximately we will get it as 1.5 kilo ohms R compensation. Because generally we will take that R compensation value is approximately equal to the RF value. So that's why we are getting this value as 1.5 kilo ohms. So by using this particular calculated values, next we will draw the circuit of practical differentiator. It is op amp with inverting and non-inverting terminals And in the practical case, we are having the R1 resistance as well as C1 capacitance. And here we'll measure the output signal, and here we are having the R compensation resistance. And here we are going to apply the input signal. And here it is plus VCC minus VEE to run this 741 operational amplifier. And this is the R1 value, this is the C1 value. So in the feedback, we are having the RF resistance and the CF capacitance. So now we will write whatever the values we have calculated till now. So here R1 value is 82 ohms. C1 we have considered it as 0.1 microfarads. And RF we got it as 1.5 kilo ohms. And CF value is 0.005 microfarads. And R compensation value is 1.5 kilo ohms. So these are the values we are calculated from the given frequency of the signal. And what is the output voltage we are getting here? It is minus RF C1 times the differentiation of applied input signal here. So this is the case when we will get if RF C1 value is greater than R1 C1 or RF CF. If this particular condition is satisfying only, we will get this particular differentiation across the output here. Always the time constant of this differentiator RF C1 must be greater than the R1 C1 as well as RF CF here. So this is the desired practical differentiator for the given problem. So next, the problem also given input signal as sine wave here. So input signal as is the sine wave, okay, with the peak voltage is 1 volt and the frequency is 1000 Hertz. This is given in the problem itself. So from this, first of all, we have to find the maximum value of the input signal, that is Vm equal to Vp into sine omega t. Why we are writing Vp into sine omega t means Vp is the peak or maximum value of the sinusoidal signal and the input signal is the sine wave. So that's why we are representing with the sine here. Okay, now substitute the value of Vp, that is 1 into sine omega, we can write it as 2 pi f. So this is 2 pi f t here. That is nothing but sine 2 pi 10 cube of f value is 1000. So that's why I written it as 10 power 3 here. So now for this input signal Vm, what is my output signal? That is V naught is equal to minus RF C1 d by dt of Vm. So this is from the circuit we are writing. And now substitute the values of RF C1. RF is 1.5 kilo ohms. C1 is 0.1 microfarads. Differentiation of Vin is sine 2 pi 10 power 3 into t here. So if we apply the differentiation, we will get it as minus of 1.5 into 10 power 3 into 0.1 into 10 power minus 6. Differentiation of sine is cos and omega value is 2 pi into 10 power 3. That is nothing but sine omega t is omega into cos omega t. So cos 2 pi 10 cube t. So if we simplify this, we will get it as 0.94 cos 2 pi into 10 power 3 t. So this is the output voltage we are getting from the given sinusoidal signal here. So by using this output voltage, we can draw the input and output waveforms. So the input waveform here it is. This is the input signal Vin with the maximum voltage 1 volt and the minimum voltage minus 1 volt. It is varying with respect to t milliseconds. This is pi, 2 pi here. So for this input signal, what is the output signal we got? Is as this is V0. This is also varying with respect to t milliseconds. So here we will get the output signal as it is starting from here. So in this way, we will get the cosinusoidal signal with the amplitude minus 0.94 here and plus 0.94 here. So this is the cosine signal and this is the sine signal we are applying to the differentiator. So for the differentiator circuit, if we apply the input as the sinusoidal signal, we are getting the output as the cosinusoidal signal. And if you observe here, the maximum voltage in the input signal we have given it as 1 volt, but here we are getting here it as 0.94. So some amount of amplitude value is decreasing here, but the frequency is same here. Both the input as well as output signals are varying with the same frequency range, that is 1000 Hz. So in this way we need to design the practical differentiator for the given frequency range of the signal. So next we will move with the second problem, that is draw the output waveform for a sine wave of 1 volt peak at 100 Hz is applied to the differentiator. So in this problem the given values are input signal is again sinusoidal signal only, that is sine wave, and the maximum voltage or peak voltage is 1 volt and the frequency of this applied signal is 100 Hz. So here in order to design the differentiator for this, again we have to follow the same procedure. The first step we have to take here it is cutoff frequency, the first cutoff frequency of the differentiator Fa, and that value is nothing but the F maximum value that is given in the problem, that is 100 Hz here. So the same thing I am taking here 100 Hz. So and again I am choosing C1 value as 1 microfarad. See, in the differentiator we are having the relation R1 C1 is equal to RF CF. So to get this particular relation we have to calculate all the R1 C1 and the feedback resistance and feedback capacitance. So and the value of Fa is cutoff frequency is 1 by 2 pi RF C. So here Fa value is, we know already, that is 100 Hz is equal to 1 by 2 pi into RF value we don't know, and C1 value is 1 into 10 power minus 6. So from this we can find the RF value as 1 by 2 pi into 100 into 1 into 10 power minus 6. So if we simplify this RF value, we will get it as 1.59 kilo ohms. So here now we know the values of Fa, C1, RF. So next we need to find the values of R1 and CF. So to find the values of R1 and CF, next I am taking the second cutoff frequency, that is FB, that is your second step. The second step we have to take the second cutoff frequency FB, and there should be always 10 times the first cutoff frequency FG. So here we know the value of Fa, so 10 into 100, Fa value is 100, so that is nothing but 1000 Hz. The second cutoff frequency value is 1000 Hz here, and the value of FP is, the formula for FP is 1 by 2 pi R1 C1. So from this formula, we can calculate the value of R1 here. So FB value is 1000 equal to 1 by 2 pi into R1. C1 value we have taken here it as 1 microfarad. 1 into 10 power minus 6. So from this, I can write R1 value as 1 by 2 pi into 1000 into 1 into 10 power minus 6. So R1 value is, we will get it as 0.15 kilos. R1 value, we got it as 0.15 kilos. And next, from the relation of R1 C1 equal to RF CF, we can find the value of CF also. That is R1 C1 is equal to RF CF. So here R1 value just now we have calculated, that is 0.15 into 10 power 3, and into C1 value is 1 microfarad equal to RF value we don't know. CF value is, RF value we took it as 1.59 kilo ohms, and CF value we need to calculate here. So CF is equal to 0.15 into 10 power 3 into 1 into 10 power minus 6 divided by 1.59 into 10 power 3. So if we simplify this, we will get it as 0.09 microfarad, and approximately I can write it as 1 microfarad. Okay, sorry, 0.1 microfarad. Yeah, sorry. 0.1 microfarads. And next we need to calculate the value of R compensation. That is the parallel combination of R1 as well as feedback resistance RF. That is R1 into RF by R1 plus RF. That is nothing but R1 value is 0.15 kilo ohms into RF value is 1.59 kilo ohms, and again R1 is 0.15 kilo ohms plus 1.59 kilo ohms. So if we simplify this, we will get it as 0.137 kilo ohms, R compensation value. So now we know the values of all the elements in the differentiator, that is R1, C1, RF, CF as well as R compensation. So by using all these values, we can design the practical differentiator circuit. So to draw that, I am taking the op-amp circuit with the inverting and non-inverting terminals. So for the non-inverting terminal only we are having the R compensation resistance, and for the inverting terminal we are having the resistance as well as the capacitor. And in the feedback again we are having the resistance as well as the capacitance. So now we will indicate the values whatever we have calculated here. This is R1 C1, RF CF, this is R compensation. Here we will measure the output signal. So here R1 value is 0.15 kilo ohms, C1 value is 1 microfarad, RF value is 1.59 kilo ohms, and CF value is 0.1 microfarads. And R compensation we got here it as 0.15 kilo ohms. So here in the output signal we will get it as minus 1 by R1, sorry, RF C1 times the integral of applied input signal. So here RF C1 is the time constant of this practical differentiator circuit. So along with this we need to provide the plus VCC as well as minus VEE. This is 12 volts in the case of 741 operational amplifier. Plus 12 to minus 12 volts we need to apply here. So for in the given problem with the sine wave of 1 volt with 100 hertz, in order to differentiate that given sinusoidal signal, we have to utilize this practical differentiator circuit. And well, coming to the input-output waveforms. So the input signal value is given as Vp is equal to 1 volt and frequency is equal to 100 Hz. So the input signal I am taking here it as sinusoidal. It is varying with respect to t, and the maximum value is 1 volt, minimum value is minus 1 volt. So for this, the output signal is so to find the output signal V0, we need to calculate here V0 is equal to minus RFC1 dV in by dt. I'm very sorry, here we are talking about differentiator, right? This is minus RFC1 differential of input signal V of t. Okay, so here if we substitute all the values, RF value is minus 1.59 kilo ohms into C1 is 1 microfarad, differentiation of sine 2 by 100. So after simplification across the V0, I will get it as minus 0.9985 cos 2 by 100 of t. So this is my differential output voltage. So by using this, I can draw my output signal as so in this way. So this is minus 0.99, this is plus 0.99. And the frequency of both the signals are same here. Frequency will not change here. In both the input as well as output signals, we will get the same frequency. And next we will see the second problem, that is design a practical differentiator circuit that will differentiate an input signal with the F maximum of 150 Hz here. So the given value is F maximum here, 150 Hz. So if we take any particular signal, that may be any signal, sinusoidal signal or square wave or step signal, anything, the frequency of that particular signal is 150 Hz. So in order to differentiate this particular 150 Hz signal, we have to design the practical differentiator circuit here. So for that, again I am going with the first step, that is the first cutoff frequency FA is equal to F maximum, that is the given frequency 150 Hz. Okay, and I am considering the C1 value as 1 microfarad here, and the value of FA, the formula for FA is 1 by 2 pi RF C1 here. So the value of FA is 150 Hz, 1 by 2 pi RF C1 value is 1 microfarad. C1 value is 1 microfarad. So from this I can write the feedback resistance as 1 by 2 pi into 150 into 1 into 10 power minus 6. So if we simplify this, we will get it as 1.06 kilo ohms. So we know the values of C1, RF and FA now. So we need to find the remaining values. So to find the remaining values, again I am considering the second cutoff frequency FB. So the second cutoff frequency is 10 times the first cutoff frequency. That is FB equal to 10 into 150. It is 1500 Hertz. 1500 Hertz it is. So the formula for FP is 1 by 2 pi R1 C. So here FP value is 1500, 1 by 2 pi, R1 value is, we don't know, and C1 value, we considered it as 1 microfarad. So from this I can write R1 as 1 by 2 pi into 1500 into 1 into 10 power minus 6. So after simplification, R1 value is 106.1 ohms here. Okay. And to find the feedback capacitance value, I am taking the relation R1C1 is equal to RFCF. So R1 value is 106.1, C1 value is 1 microfarad, 1 into 10 power minus 6, and RF value is, we got it as 1.06 into 10 power 3, that is kilo ohms, and we don't know the value of CF. So from this, CF is equal to 106.1 into 1 into 10 power minus 6 divided by 1.06 into 10 power 3. So CF value, we will get it as 0.1 microfarads. And next we need to calculate the value of R compensation, that is equal to R1 parallel with RF again. The R1 value is 106.1 into RF value is 1.06 into 10 power 3 divided by 106.1 plus 1.06 into 10 power 3. So this value is 96.4 ohms, R compensation values. Okay. So by using these values, we can draw the practical differentiator. Okay. Minus plus. For the non-inverting terminal, only R compensation. For the inverting terminal, one resistor and one capacitor. And in the feedback, again one resistor and one capacitor. And here we will get the output signal. So now we will write the values of all the resistors and capacitors. So R1 value is 106.1 ohms, C1 is 1 microfarad, RF is 1.06 kilo ohms, and CF is 0.1 microfarads. And R compensation is 96.44 ohms. And supply voltage is plus 12 and minus 12 volts required to run this practical differentiator. So it will run with minus RFC1 differential of input signal. So in this particular problem, they didn't ask for the output waveform. So that's why we are not drawing the input and output waveforms. Just we are designing the practical differentiator circuit to differentiate the given 150 Hz signal. So next we'll move with the next problem. So here in the differentiator circuit, the input is a sine wave with peak-to-peak amplitude of 3 volts at 200 Hz. Sketch the output waveform. So in the previous problem, in all the previous problems, we designed the practical differentiator to differentiate the given signal. But in this case, they given the signal, just we need to draw the output waveform for that. No need to draw the practical circuit, just we need to draw the output signal. So here the input signal given it as sinusoidal signal again, sine wave with the peak to peak voltage is 3 volts and frequency is given as 200 Hz for that particular signal. So by using this peak to peak value, we can calculate the maximum input voltage Vm. Maximum input voltage Vm equal to Vm sine omega t. So here, first of all, we need to calculate the Vm value. Vm is equal to V peak to peak by 2 here. It is nothing but 3 by 2, that is 1.5 volts here. So 1.5 volts in the positive direction and 1.5 volts in the negative direction, positive peak as well as negative peak values. So here input signal value we can calculate here it as 1.5 sine omega t. So here I am replacing omega with the 2 pi f, that is 1.5 sine 2 pi f t here. And what is my f value? 200. So substitute that f value here, 1.5 sine 2 pi into 200 into t. So after simplification, my input signal as 1.5 sine 400 pi t ohms. So this is the input signal given. So for this, we have to draw the output waveform. So for that, the output of the differentiator I am taking now. So the output of practical differentiator is V0 is equal to minus RF C1 d by dt of V applied input signal. So now here I am taking this value as A here, A equal to minus RF C1. So why I am considering it as A as some constant value means here we don't know the value of feedback resistance as well as capacitance values. So that's why we are taking here it as A. So V0 equal to A d by dt of Vn. So now substitute the value of Vn, whatever we calculated in the previous slide, that is A d by dt of 1.5 sine 400 pi. So after applying the differentiation, we will get it as 1.5a into 400 pi cos 400 pi t. Okay, this is the output signal for the given input signal V in here. So here the output is the cosine wave of same frequency. Frequency is not changing here in the input signal 400 pi t and in the output signal also 400 pi only. But the amplitude of the output signal is depends upon the values of RF and C1 here. But we don't know that value, so that's why we are not taking that. So if we draw the output waveform for this given input signal. So the given signal I am writing first. Sorry, I am drawing the given input signal V in. It is the sinusoidal signal. Okay. With positive peak is plus 1.5 volts and the negative peak is minus 1.5 volts. So total 3 volts peak to peak. The signal is. So for this, the output signal is for only 1 second. I am drawing here. This is V0. This is also varying with time period and it is also varying with time period here. So here we will get the signal. Okay, so here I mentioned here it as we don't know the peak to peak value here. Why? Because that is depending upon the R1 CF value. So that's why we are not mentioning any output amplitude. But the time period, that is 1 by f, is 5 milliseconds. The time period is 1 millisecond in both the input signal as well as in the output signal. But the amplitude, we don't know how much we are getting in the output signal. Why? Because we don't know the value of feedback resistance as well as capacitor. So in this way, we need to draw the output signal for the given problem. So in this session, we have discussed what is meant by practical differentiator circuit and what are the problem related to that. In the problems we are having two categories. One thing is designing of the practical differentiator circuit from the given frequency signal. One thing, from the given frequency signal, we need to find all the resistance and capacitance values of the circuit, and we need to draw the practical circuit along with the input-output waveforms. In the case of second category of problem, just we need to draw the output signal for the given input signal. No need to draw the practical differentiator circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.